My name is Heinrich Bockhorst. I have quite a long history working with zip, starting from the last millennium, where I was at the compute center in Hanover, and these were tightly coupled to zip. Already that time, it was already before the HLRN was founded. So the purpose now is to talk about VTune Profiler. And let's go to the agenda. So first I would like to do a short introduction and showing some of the default slides from VTune Profiler for people who have not seen it before. And well, after that, there is already a short preview on the GPU hotspots profiling, on the GPU profiling. And then I will talk about the suggested GPU analysis types. So when you just open the tool and browse through the types, then it might be confusing, even for me. And we got a presentation, I guess, 2 weeks ago from a specialist or from the developer who's shown us which one are the most interesting analysis types to use and how to use them. And by the way, I'm working with the Gromacs team at KTH, and they're still a little bit reluctant to use VTune because sometimes the timing data seems to be a little bit confusing, but I guess with the developers we get it working. And it's very nice to have even source view for inside the kernels, because the kernels in Gromacs are quite large compared with other codes for GPU usage. And I did my testing here on the dev cloud. So first reason was that it didn't work on our lab machine. So we have to analyze what is the case for that. And the second is that you can redo the experiments with your code and know what is working and what is not working or should work on the dev cloud. And we will work on improving it, and even with the next update of VTune, there will be more support for the level 0 backend, for example. So it starts all with the OpenCL backend, but level 0 will take over, and it will be the backend for the future of Intel hardware. So I will show experiments from Gen 9 and DG1 and probably do some comparisons here. What changes when you go from Gen 9 to DG1. So here is some more marketing-like slides here about VTune Profiler, but just for the completeness. You have here some facts listed about the features of VTune Profiler, like which languages it's supporting and the OSs it is supporting, and yeah, the diagrams you have. And on the right upper end, by the way, was there a poll done? So I haven't seen it here in presenter mode.
We can do it if you prefer. No, we can do it now.
So
I started a poll about the VTune usage.
Thank you. Because maybe it's interesting to see who has already used it and who is using the. Oh, that's pretty good. So I was trying, I will talk about later to use the CUDA tools. And maybe good to have some people to ask how they really work. Okay, let's proceed. So you see on the right upper window, you see the first screen when you choose for an analysis type, and the performance snapshot that has been a separate tool before is now integrated into VTune. And the idea is that you have an analysis type which gives you overall information about your code and handling all the different topics here for the different analysis types. And even better, it makes suggestions which tool to use next. So when you do the performance snapshot, and it has even a GPU branch now. Sorry, I haven't tested it because last time I tried it, it didn't work, but that was on under NDA soft hardware with the Arctic Sound card. So the performance snapshot is the first point here, and then it will hint which analysis is interesting for the next step. So when you have a GPU running, it will show you. Now I can try. It will show you the GPU compute hotspots as interesting, and maybe the GPU offload. I would touch the GPU offload here because maybe the topic of GPU offloading is or the offload scenario is better handled by the advisor my colleague will show as the next presentation. And so you see it's even possible to get source view. And with source view, it will classify which or show you which instructions it has. So here the yellow bar or orange yellowish bar is showing you how many instructions are integer and floating point 32-bit. And the blue bar here is for the memory and the synchronization instructions. And what is also nice is for each kernel you can generate a diagram below here that gives you information about the active execution units, but even more interesting, the memory bandwidth between the EUs and the third level cache or the shared local memory. So for Gen 9, this are the same, but more interesting for GG1. And unfortunately, it wasn't, the diagram wasn't working here for DG1, but it will be working in the future. So, and here, this here is more what goes over the PCI. The write bandwidth here to the last level cache, and the read bandwidth here. And so you can visualize this in a nice diagram. And besides, so many people, what was a little bit another world because I'm coming from HPC and we were working more command line focused on clusters where we don't had X windows or it was tedious to use them. And so we were working with command line, and the people from VTune, they always showing Windows and GUI. And so it's good to know how to generate the command line from the GUI or have some command lines that you can test separately. And it's now possible to do remote profiling. I haven't done this for this presentation, but it's worthwhile to test it. So you can use your in a browser VTune and run it on a remote machine. And yeah, these are new features. So this is a more marketing-like slide. They like these pictograms. So you can profile single thread, multi-thread system. And what we want to do is today this media and OpenCL application, which also includes now the DPC++ applications. There is much work was done on HPC and cloud. So it's because of the virtualization hard to get directly on the hardware, and there were some workarounds found to use directly the counters and get VTune running. Then there is memory and storage management. What is not directly covered here is the new I/O analysis that we are currently testing internally, which gives information for example, from the PCI buses. So it measures all I/O like network cards and so forth, which can be interesting for HPC. So it's very well proven, the analyzing and filtering features that we have in VTune, and we could integrate it in your environment. Either when you like in IDEs, and you can use Eclipse on Linux or Visual Studio on Windows, and you can use command line and maybe build regression tests by using command line. So I was probably, there are some people yesterday. There were some people from Jülich present. They have a nice framework for benchmarking called Joop. And I was able to have some kind of integration from VTune into Joop, that I got the VTune data here automatically. So here's another glance on the so-called bottom up, which is the most interesting or detailed information you can get. And you can see here, for example, the name of the functions or the kernels that you are using. Then you get a breakdown if it's about the utilization, which is also showing you the parallelization here. And then for threaded applications, you can see the imbalance time and so forth. This is could be used as OpenMP analysis, and the overhead time, and then you can have information about the microarchitecture. And on the bottom, you see that for each OpenMP thread, there is a timeline here, and brown is usually good, which is CPU time. So CPU is doing something meaningful. Green is, it is running, but probably it's just sleeping and not using the CPU. And red is overhead, so spinning and other stuff that can happen and which you want to avoid. So generally, it's that you are trying to minimize the red part here. And it gives you a summary with some overview about all the features from where you can go on. So we have two ways to collect data, and probably you should say it's three ways to collect data, because the first one is the software collection. and this needs no drivers, so it's easily applied to any processor where the software can be installed or ran, and it can be even used to compatible processors from the competition. So, but not, of course, with all the features. So this is just that there is no blocking of features, but it's also no, of course, no support from our side for competition processors. So the default resolution is here 10 milliseconds, which might be much too coarse for good information. And for better granularity, you have to use the hardware collection. The hardware collection uses directly the performance monitoring units and all the hundreds or thousands of events that you can generate here. You can either collect system-wide or you can collect just a single process. The default resolution is 1 milliseconds, and finer granularity is even possible, but then on the other hand, you generate more data. So you have to think about if you can, or if you have a fast I/O, you might want to generate more data and have the fine granularity, or vice versa. So this requires a genuine Intel processor for collection, and you can collect stacks, but have to switch it on in the configuration diagram. So it works also with VM in certain for certain VMs. Here, this vSphere and KVM, and so you can have even data there or access to the PMU. And it uses either, and that's why I said 3 ways, either with the Intel drivers, or most people or centers are a little bit reluctant to install the drivers on each node. But the Linux perf drivers are almost everywhere installed, so you can use the Linux perf drivers. And the difference is not so crucial. It can be crucial when you have a very new CPU that the Intel drivers support it first, and you have to wait until perf is catching up. But most times it's perfectly okay to use the perf drivers. There's no special recompiles here, and you can analyze different languages, and for each you can also have a look at the assembly. And normally it works, but here for my GPU experiments, it did not work. You can link the source code to the assembly. So you can also learn about assembly by clicking on a source line and see what the assembler does with it. So here's just another overview slide, and this gives a little bit more information about the filterings and viewing options. So you have plenty of filters, and sometimes it takes some time until you find out which one filtering is the best for your purpose and which you like. So it's a matter of taste, or it's a matter of the problem you are facing to choose the right grouping and the right filtering. So grouping is adjusting the data grouping, so you can either have functions and call stack, that would be the default, but you can also add the source function, or you can synchronization objects in certain analysis types, or you can even view the core where it's running as grouping. And Well, if you double click, if you have compiled with -G or with debug symbols on, and you double click on the function name, you will even see the source code, and with a second click you can see the assembly. Again, it tries to judge if it's the utilization, which is also quite synonymous with the parallelization, and you can judge if it's okay, if it's ideal or poor, or it's better than ideal, which happens quite rarely, but it happens. So most of the times you will see very large poor bars here, because it is focusing on all the logical threads that you can have. And when hyperthreads can only have increased the performance at best as 30%, it's very unlikely that you see ideal scaling over all hyperthreads. So it's probably, but you can change the diagram and change the meaning of these colors. So here you see the worker threads again, and you can even filter here and select timing regions and see the diagrams due to the new filtered timing regions.
Mr. Bockhorst, we have a question.
Yes.
Has asked if VTune offers some way to tune the program on the fly, so without actually doing any manual code changes, so that one could try out something on the fly, so to say.
No, that would be a very good idea, but we are not that far, so it's that would be some good feature request. But that would be really advanced if we can do this.
Okay.
So it's more that you see VTune as the perfect thermometer, or how shall I say, the perfect tool to see all the effects. But in the end, changing the code and taking consequences is more your step then, and you just use this for analysis. Would be an interesting idea to see this maybe combined with artificial intelligence to do the on-the-fly changes. So this would be the source view already with clicked on assembly view. And here in this case, this is for the Windows assembly, though the assembly will look different on Linux. Or you can also have the assembly then for the GPUs, which is probably a little bit easier to understand, but I still have to have more time practicing on it. But it's you will see it later how it looks like, and you can click on here this line 573, and for this line you will see all the assembly that is generated for this line. And maybe the ideally this times here for the instructions would sum them up for the time that we have on the source line. Could be about right. So so we have here kind of a heat map. So when you have the full source code, and then you can go to dark blue parts of the heat map. That's the part where most of the time is spent. So for quick navigation, you can use the heat map, or you can even use this here for hotspots to navigate quickly to the largest hotspot or the smallest hotspot and so forth. So these are all nice features to make life easier. And here the command line. We see it later in more detail. You can have a button here on the left lower, or yeah, somewhere below the analysis configuration, and you can use this to generate a command line. So if you want to work on a cluster without X vendors, you can open the GUI on your laptop or on your Linux desktop and generate your analysis. Click on this button and then it will present you here the command line. It probably puts a little bit too much into it, or all the path search directories that might be not necessary, but at least you get here the collection mode and other flags that you need for doing the command line analysis. So interactive remote collection, I haven't done this. Sorry, I wanted to try it once and tell it here to you as well. But it's possible to run Linux in a browser window and then do a remote connection to a cluster node or whatever to analyze. So this should be working, and you might give it a try if you have all the credentials here to log on the remote node. So just another overview window. I think we can keep this short. Here is something about OpenMP scalability, and you can build here diagrams about the time spent in different levels of parallelism. So if you have 4 threads working in parallel, it measures here the time when 4 threads are running in parallel and so forth. And you have the timeline here again, and you can filter out different regions and get closer information and more details. It's, by the way, interesting if you use the software collection and later on do the same experiment with the hardware collections and then see how the coarse-grained structures here are getting into fine-grained structures. So what we want to hear today is about GPU profiling, of course. And the new 2 GPU analysis types in the one API version is that you have GPU offload. I won't cover it today. And the more advanced is the GPU compute media hotspots. And that you can use to get even source line information. So we are not, I'm still a little bit skeptical if this all works really good, but we are still in the phase to understand how it works and what kind of information you can trust and which one is where you have to be a little bit skeptical. But it gives you a first indication where interesting things happen in your source code in larger kernels. Yeah, with the CPU offload, it's more the interplay of the CPU and the GPU. And probably it's better to, or more obvious when you use the offload advisor, which comes in the next presentation. But we will focus here on the GPU compute media hotspots. And that shows if the kernel is efficient and shows all kind of bandwidth that you have in your system. So you start always with a summary page, and from the summary page you can go to other stuff. So you see the execution unit array stalled idle. So we have here 94% of the elapsed time is idle. So it's colored in red. So you have, and the flag is going up. So you should see what you can do about the occupancy here and how you can increase the usage of your execution units. So this is already quite interesting, and we see it later in the demo. This example is here for matrix multiply, and you see a timeline here on the top for the master thread or whatever that is in interplay with the GPU. And the upper part here is for GPU. And here you see just this pink bar here. And when you zoom into it, you can even see individual kernels, what we can do later in the demo. And the lower part will focusing on the work of the host API. And so here you cannot read this, but this will be the CL build program part where the host is building the kernel program. And all this stuff can be seen here, and even data transfer you can see when it happens before a kernel and get some information if this is running well together. And then you have some, unfortunately, this is more an quite ideal example. So you see here a bar for the execution units, and this shows that they are running at about 100%. And normally you see some green stuff for, no, it's kind of strange here, but because the green stuff should be the one showing running, and the red stuff above should be showing if it's idling or stalling. And the next point here is showing how many threads are scheduled, and this should be high. So when you have a high occupancy, so all threads are running and not idling. The instructions here doesn't seem to work really good. So then we have some memory accesses here, and it prints the maximum here for your convenience. And here is the GPU L3 cache bandwidth. Unfortunately, no number is shown, but we should have a real example later. And the GPU execution. So this is again the diagram, but I think I won't spend too much time on this again, and better show later the real stuff. So this is about the source view, and you get here really the source lines on in your kernels and the estimated GPU cycles. I can explain a little bit more how this is done. So it's kind of, it's called estimated GPU cycles because it cannot measure here really per instruction, but does have some logic to estimate the number of cycles. So I was running Gromacs on DevCloud. So I'm working together with another Intel engineer with the Gromacs team. And they have now, a month ago, a version of Gromacs delivered running on SYCL. And you can download it. I will give the link. And this new SYCL release of Gromacs was using the OpenCL infrastructure first. So they have a GPU infrastructure. There was with their device manager and testing of the kernels and the GPUs first. And they now transformed this to SYCL, but in a different way than the project we heard before, because they were not using the compatibility tool. So they wanted to do this all manually. And they started from the OpenCL infrastructure and then ported the data transfer. So it is not too much different, or it's quite the same from OpenCL and DPC++. And so that was not too involved. But if you have seen the Gromacs GPU port, so this is really high-end stuff, what they did. And in CUDA, they managed to run almost the whole program on the GPU and just need to offload things to the CPU. So we want to reach this state maybe next year for the SYCL port as well. So almost 90% of the work was done for doing the new infrastructure and the abstraction of the different GPU branches. We have now a CUDA branch, an OpenCL branch, and a SYCL branch. And the idea is to exchange the OpenCL branch completely by the SYCL branch, because even competition will have SYCL versions on their GPUs, and so it makes sense to have just SYCL instead of having a SYCL and an OpenMP branch. The kernels, as I said before, were ported directly. No compatibility tool was used, at least what they said. Maybe they tried it to see what happened, but they did not tell. I was showing them how it works, but never heard back if they had tried it on their own. And tested by me was after I received this version. So there were some preliminary versions even around Christmas. And then the release version that you can download was last month released. And I tried it with the one API ICPX compiler. So you might ask, why not using the DPC++ compiler? And in the beginning, the DPC++ compiler was not having OpenMP. And OpenMP, is crucial for running Gromacs and scheduling the different kernels. So we needed to have the ICPX compiler, which has the same functionality as the DPC++ compiler. But I think Igor said it yesterday that it's less convenient to use the ICPX, but it has probably more flexibility. And then I was doing my own LLVM CLang compiler. So you can download the LLVM CLang compiler with the SYCL branch and from Intel and build the latest branch. And that was necessary because some features were even changed here, which were crucial for Gromacs to run, and they found some bugs in our compiler, and so it's good to have this own compiled LLVM compiler. Then in the end, as the other people already said, there is the CUDA backend compiler, which I was able to run on the Jülich system. And then you can even use the CUDA tools to analyze the performance. So the next bullet here is the address for downloading this version. So it's an official version. It's not in the release yet, but hopefully in the next release we will have it directly included. So it was a little bit too dangerous and too many changes, so they didn't want to risk that and have SYCL not in the main version of Gromacs yet. So what I wanted to suggest is the next talk at the eVocal conference. I have not seen the list of talks, so they are still reviewed, but I'm pretty confident that they will accept the talk from the Gromacs people about their porting efforts. And please stay tuned and watch this. So this will be really interesting. So they're really good in this, and Gromacs is really one of the lighthouse codes for GPU transformation. So that is my my default configuration here with CMake. Hope you can read this. And the new stuff is that you have GMX GPU equals SYCL. And yes, using here the ICPX compiler, maybe it's you can do this in another way. And I don't know if this by default adding a -G here to get all the symbols visible. So the VTune GUI is already in the base kit available of one API. You can use the command line for batch systems and so forth. And the command line can be generated also by the VTune GUI if you need this. And the VTune GPU analysis is still experimental, so there will be some shortcomings and some new branches will not work as expected. But I think when everything is really mature, then this will be a really powerful tool for analysis of your GPU performance. So that was here one of the error messages that I got, but some of the developers told me that I should ignore most of these warning messages, but here this could be a little bit more crucial, that there are some configurations missing where you have to be root to do this really. So let's go to the demo. And now I would like to stop sharing this and share my VTune. And I was choosing to do the VTune here on my laptop for the best visualization, but it's probably quite identical to do this on a Linux desktop. So what I did then was to generate some data on the dev cloud and tar this and draw this on my laptop, and now I can analyze it here. And so I stop sharing this and share now my VTune client. Can you see this?
Yes.
Thank you. The first point would be here. This would is how it comes up when you load it by doing new analysis. Then you get this. So I'm a little bit reluctant to do this because sometimes it erases all the things that I did before. So when I load a new analysis. So believe me that this is the window that comes up when I do this. And first thing to proceed is to have an executable. So here I'm just faking an executable just to satisfy this menu, because otherwise you cannot go on. So this is some Fortran example, but never mind. It shows here then as the first analysis type the performance snapshot. And when you click on it, you see this tree that we've seen before about the analysis types. And you can do the performance snapshot first to then the interesting next steps will be highlighted, or you can directly go to the preferred analysis types. So you can go here to GPU offloading or GPU media hotspots, and you always get, when you hover over it, more information about it. And we choose here the media hotspots, and the first thing is would be overview, and you see there is about no overhead, and the dynamic instruction count will be the most demanding instruction, and this is one that induces really high overhead, and you cannot, it's probably even not enough here, the 3 bars here, it's really factors slower than, but you get most information by that. And if you want to lower the overhead but see most details or almost all the details, then you can go here to source analysis, and then it will time the basic blocks and estimate the timing for each instruction. So it does a timing for each basic block in the assembly, and then it estimates which is the share of each instruction inside this basic block. But when you look at it, you sometimes see that they all get the same timing then. So it's probably at first guess, but this is a way to lower the overhead. And the other interesting would be the memory latency. The memory latency will do almost the same, but only for the memory instructions. So it will not time all the the compute and other instructions, but will only time the synchronization and memory instructions. Why is it done? Even for the overhead. So this is less involved to concentrate just on the memory. And so you do 2 analyses, one for all instructions and the other one just for the memory, to get a clearer picture here. And as I said, you can here on the bottom part, you see a knob here for generating the command line. And when you have done an analysis, you can click on it, and then you get the command line options like -collect GPU hotspots. That's the first. And then you have 2 knobs. Is the profiling mode source code analysis, source analysis, and then a knob for source analysis equals mem latency. And the other stuff is just some additional paths. So it's most of the time it's not necessary, but for completeness, here they show this in the command line. So let's go to my predefined experiments. So the first would be just the, sorry, going here um, to the summary page. And that was just collecting GPU hotspots and without anything else. So this is just a course overview. And you can see here the different kinds of bandwidths, or the first information, of course, is here the execution units, staled and idle part. And this 18% is quite low when you compare it to the slides from my colleagues. There we had something of 80% or so. Here they really managed to get all the execution units running. And so it's not painted in red anymore. And you can see the floating point utilization as 50%, which is probably not so bad, because I have taken here a very small, just 100 steps. And some other people who are benchmarking these results take 10,000 steps to get reliable numbers, but then the VTune X result directories would blow up. So I just taken 100 steps here. And, the values will be even better if I take more than 100 steps. Okay, and you see some information here about the platform and the other informations. So here you can see, maybe this is too small here to read this, the command line. And I was not using here because I wanted to concentrate on the GPUs, not using an external MPI like Intel MPI. So they have an internal thread MPI, which is interesting. Though it's just one process, but it behaves like MPI and uses the MPI stubs to distribute the work. And yeah, using a free data set that you can have from the Max Planck Institute in Göttingen. And yeah, giving some further information about the GPU and the CPU and the OpenCL version. But this is all not really interesting. The real more interesting part comes here. And you have here two knobs here, one for the memory hierarchy and the other is platform. Memory hierarchy, here on the lower part, you see the kernels. So these are the non-bonded kernels that we have in Gromacs. And you see the total time in these 100 or 99 is it here for the instance count, but it was 100 iterations, but doing two kernels that are almost the same, but doing slightly more work for calculating the energies. And you see here some information about data transfer, about the staled or idle time of the execution units, the number of threads that were started, the L3 bandwidth, and the L3 to GTI. GTI is the GPU transport interface. That's the last interface before the PCI. This is the bandwidth between this interface and the L3 cache of the GPU. And then you have measures of the local shared memory, the GPU bandwidth, which is what comes over the PCI bus. And when you click on a kernel, it changes the diagram on the top, and then you see new numbers here. It's still loading. New numbers here, and you can find here the read bandwidth of the GPU as 3.1 gigabytes. You can see in the grid as well, and also the write bandwidth of 900 48 megabytes per second is here the right bandwidth. So this is nicely showing you the different aspects or the different hardware components of the grid. So the other option here is to go to platform instead of the memory hierarchy diagram. And then you have the trace here. And you see that's just in the beginning, a lot of initialization phase. So this is far too small section to do really benchmarking. So you need far more. So normally for minimal benchmarks, I take instead of 100,000 steps. But here I didn't want it to blow up the result directories. And here you see the execution units. And when you hover with the mouse over it, you always get a concrete number here of the active EUs, the idle ones and the stalled ones. And yeah, then you have different measurements here for the threads that are started, and you can do this for all time slots. And you can, to see it better, you can do a zoom into it and zoom in and filter by selection is here probably the best way. So all the stuff in the grid below will be adapted to this. Takes a little bit to compute this. And then you can see even the individual kernels here. So the kernel invocation for each time, and you see this is the non-bonded kernel. So by the way, in Gromacs, this non-bonded kernel takes normally with normal workloads about 90% of the time. So that's why Gromacs was such a good target for doing porting to GPU, even though the program is really involved and big. So the main compute kernels are quite sharp, and you can do 90% of the work by just adapting this kernel or some variants of this kernel. Later on, they will even try to, or they will port all the other kernels as well. So was there something, I haven't the chat open here. Was there some questioning or so I see?
Yeah, but there are also some answers was about terminology and about vocabulary, so to say, used how to make sense out of all the terms. Yeah, but your colleague Michael Steyer answered.
Okay, did I say something wrong or?
No. It was just lots of jargon, so to say, in these menus and so on. Yeah.
Okay, thank you, Michael. So you can see here the individual kernels. And when you go into it, you can see even small kernels here just for, well, this is also compute kernel, but you can also see some kernels here for enqueuing the write buffers. And on the lower side, you can see the actions of the host. So the host API. Here we have some wait statements here from the host, where the host is waiting until the kernel is finished. And then we have here some memory operations. And in the beginning, you can even see the build of the program by the JIT compiler. So we have here the execution units, and green means they're working, red means idle, and so on. And we see the instructions, and of course we see a pattern here. It's up when the kernel is running with the EU instructions and going down when only the host is working. And then we see all kinds of bandwidth here, and all with the current value here. And so this gives really a lot of information. The L3 cache on the GPU and even the cache misses, but it looks like it's yeah, pretty stable across the kernel. Here it's a little bit different. Maybe have to investigate what happens here. And we see here the shared local ban, the GPU utilization on the bottom, and the GPU frequency is measured. And the kernel timings here are adapted to the kernels we see. So we see here only 14 kernels issued here. And what I haven't shown, in the end, we get even more information. And in the end, you see the synchronization, like the GPU barriers and the GPU atomics and the cache misses of the L3. So let's proceed. This was the less involved GPU hotspots without anything else. And by the way, this was done on Gen 9 hardware on the integrated graphics that you probably already have yourself in your laptop. And so this is also from the integrated graphics. And yes, but this is the most involved analysis. And here we have the summary, and we have a short summary of all the kernels it sees. So these are the main kernels, as you see here, the one that is taking all the time, and this one invocation here with more time is that just it's more or less the same kernel, but with additional calculations in it. So how does it look here in graphics? So this is again the timeline. I think we don't have to dive into it. The blue part here is a CL build program where the JIT compiler is building the program once in the beginning. So it's crucial to have many iterations here, because otherwise your benchmarks will be spoiled by all the beginning phase. So this is the main kernel again, and you get here more information like the global work size and the local work size, the timing, also the mix of instructions. So you see the red here is the control instructions. Then we have integer 16 byte. Okay, don't know where it happens. And we have the yellow one is the integer 32 ins and floating point. And then we have the SIMD utilization. I think this question came up before. And here it really measures how well the different lanes of the SIMD registers are utilized here by the code. And 70%, I think it's quite good. And there are some other kernels which really reach 100%. So this is a real good mix and a real good use of the hardware. And so we can go on. And now let's see, how does the source code look like? So probably we do one previous experiments. Here we have inline mode, hide inline functions. And this is most of the time good, because when I Otherwise, it will show all the timings for different API functions and will not show in the source code how much they take. So I will go to show inline functions and then go to this kernel. And then it will show you for this kernel everything that was used in the kernel. So you see the different accessors here for the buffers. So by the way, they were still, they were preferring to use open or DPC++ buffers here. Because first reason was that until the latest standard, it was not officially released that USM interface. Maybe they will switch to it, but other people say they like the buffers better because it's more C++ C++ usage when you use the buffers. So you can see a lot of AP calls, and most of it goes here. So I have to see what this is. Really, so this is a little bit involved, and I must admit that I haven't understood how to interpret this stuff here. And the demangling is not working here. So this will leave some further investigation. But let's go to the source code. And for source code, it's better to hide the inline functions. So now they are gone, and you can double click now on the kernel name. And you get the source code. And by the way, I prepared this already. And when you do this first time and you have moved the data, then it will ask you for the location of the source file. So when you do it, the analysis on the same machine as where you generated it, this is no problem. But when you move the data, it will ask you for location of the data, and then you can provide or browse for the source code when you move this as well, and tell it where the source code is located. And here you see a message source file is saved in the result cache. So when you've done this once, it will show you, it will keep the source code information inside. And here we have also this instruction mix here. And we see here for the Lambda, this is all control instructions. So you can, my favorite source line was a little bit, so you see here, this has to be probably further investigated because you see it not only in Gen 9, but also in DG1. Here is a bool calculated that's necessary for the further control flow. And it seemed to be very expensive. And then you can, so my favorite part here from DG1 is not looking too involved here. It's either this if statement. So this is molecular dynamics, and they have to work through the pair list. But here it's a little bit smarter because they build clusters of atoms, and so they go through clusters, which make another level of blocking here on the GPU, and this speeds up the performance a lot. And the question is, one parameter that can be changed would be the cluster size here, and you can give it. So the cluster size is smaller or half as small for Intel GPUs compared with NVIDIA GPUs, because we don't have the number of registers here. And this is probably one performance gain when we have enough registers to double the number or the size of these clusters. So there's one if statement here, and this statement here where things is copied to the local shared memory on the card just by copying from this array to this float for data type, so the four floats here for further usage, and it has some impact. It doesn't look too bad here. It's all memory, but I will show you later how this looks like. Maybe I speed up here a bit, how it looks like on DG1. That would be the same experiment on DG1. And here it's only half the time, but this time, forget about it. It's with very high overhead. The other experiments will have less overhead. And yeah, you can now go here into it and searching for the same line. And I found this interesting here because it's here really copying on the shared memory, but it also shows that there are some synchronizations here for copying it to the shared memory. And so I have to talk to the developers to really understand what happens here. And here, this if statement, it's much more expensive on DG1 than on Gen 9, and it has a lot of control flow instructions here, which were not shown on Gen 9. So I think I don't have too much time left.
Yeah, we should wrap up in about 5 minutes.
Okay, yes. Sorry for that. And so I will go back to the presentation and close this. Maybe if it's wanted, I can give you the provide you the experiments, but it's quite easy to yeah, you don't have the executable yet. I can share the result files with you. So here is the command lines I used, and I took a few screenshots from the experiments before inside my presentation. And what I haven't covered yet was the source code analysis with the memory. But that was interesting to show that this line here is using 13% and 20% on Gen 9. Summary. So VTune provides, oh, this is not, what did I do? So VTune shows you about kernels and even up down to source line instrumentation. The full dynamic instrumentation has very high overhead. So it's just for information, I would say, to see where something is happening. The source instrumentation might be better to do real benchmarks, but it's more or less, it does estimates for the time for each instruction. And I forget to show you the assembly. So the assembly even shows for each line the SIMD occupancy would be interesting as well. And don't forget about the memory latency here. So there's an extra source instrumentation just for the memory. Now, if you have, sorry for not stopping in between, but if you have still some questions, I would be open to it now.